Okay, good morning, everyone. Let's get started. So today's going to be our last class. So we're going to be covering acids and bases, which is exciting as a topic, but it's also exciting because it's our last class. Now, just wanted to bring us back to the schedule because, it's easy to get lost during remote learning. But in terms of what we have left to do, have assignment number 9 just due this week, and assignment number 10 due next week. You have a final extra credit discussion board, and your final draft of your Chem Wiki is due. You have a post lab and a lab report due as well, and you'll finally have your exam. I will send it out next Friday. It'll be available on Blackboard, so you have 72 hours to complete said exam. So, go live Friday at, I don't know, probably 9:30 in the morning, like when this class starts, and then it'll be due Monday morning at 9:30. So you have full 72 hours to tackle exam 3. It's going to be the same as the first 2 exams, multiple choice, and nothing exciting. It's an exam. So the final thing I just want to make mention of is that I will be adjusting the grades for one of your exams. So I'll let you know if in an announcement how the grades will be adjusted for one of your exams, just because I have to sort of even out the exam grades because they were a little bit low. But I will let you know that via an announcement on Blackboard how I will be adjusting your second or first exam, one of the two, probably your first exam. All right. All right, let's get started with this acids and bases. It's kind of a fun type of course because it's very relevant to sort of your average everyday life. You sort of don't think about acids and bases, but they really are everywhere. And understanding what they are, how they work, and all that fun stuff sort of just kind of opens up, your, I don't know, your mind, I guess, to what's going on in average everyday life. Like, I feel like I answer a couple questions every week or so about an acid and base question from someone in my family. So I feel like this is a good set of topics we're going to cover today. So, but when we're thinking about acids and bases, the earliest definition was given by Arrhenius. Now, we haven't covered Arrhenius before, but he's a really important physicist and chemist. As you progress in potentially physiology, you'll learn a little bit more about Arrhenius. If that is, of course, if you go the route of physiology, of course. But Arrhenius gave this early definition, and we don't really quite use it as much anymore. But Arrhenius' definition of an acid was anything that contains a hydrogen atom and dissolves in water to form a hydrogen ion, i.e. a positively charged hydrogen or just a proton. So we can look at Arrhenius' definition for an acid. Hydrochloric acid dissociates itself into a hydrogen ion in an aqueous form and a chlorine ion both as well as in an aqueous form. Now, a base contains, according to Arrhenius, of course, a hydroxide ion and hydroxide and dissolves in water to form a hydroxide ion. So we have sodium hydroxide as a solid. It dissolves in water to form aqueous sodium and aqueous hydroxide, with the key here being the hydroxide, the OH minus here, and the proton being the indicators of a Arrhenius acid and base. But Arrhenius wasn't perfect, and it does correctly predict the behavior of many acids and bases, but his definition is ultimately limited and can sometimes be inaccurate. So, for instance, hydrogen ions actually physically don't exist in water. He didn't know that, but we know that now. Hydrogen ions actually react with water to form hydronium, H3O+. And so you can look at this chemical reaction, hydrogen ion, so you can pretend like you got it from HCl. It reacts with water to form the hydronium ion, and it's typically, again, present in aqueous solution, as you can see. So Arrhenius was not quite right, but he was on the right track. It led us to Brønsted-Lowry, or Brønsted, if I'm my Danish is serving me. I think it's Brønsted-Lowry. But Brønsted-Lowry said that a acid is simply a proton donor, so it just donates a proton or a hydrogen ion. And a Brønsted-Lowry base is simply a proton acceptor, so accepts that proton. So we can look at this hypothetical situation where we have hydrochloric acid being a Brønsted-Lowry acid and water being a Brønsted-Lowry base. Now you'll notice that the hydrogen ion tacked onto chlorine here dissociates and it tracks onto the water here, making the hydronium ion. And then that we have our single chlorine charged ion here. So water's our proton acceptor, hydrochloric acid, HCl, is going to be our proton donor. So we have a Brønsted acid and a Brønsted base. So much more accurate definition of what an acid and base is. But when we're thinking about what a Brønsted-Lowry acid must contain, it has to have a hydrogen ion. So we write a Brønsted-Lowry acid simply denoting it as HA, with hydrogen attached to some functional group. So in this case, we have hydrochloric acid, HCl, hydrobromic acid, HBr, nitric acid, HNO3. Now, we also have sulfuric acid, H2SO4, or we have something that you guys probably know, acetic acid, which is just vinegar, which is HOOCCH3, right? So acidic part of acetic acid happens just to be this hydrogen atom. It's not all the hydrogen atoms, because these hydrogen atoms are going to be in a stable relationship with this carbon, but this one that's bound to an oxygen is actually not in a stable form. So you can have multiple hydrogen atoms attached to one given Brønsted-Lowry acid, but only one of them is going to be acidic. And in the case of sulfuric acid has two hydrogen atoms attached to sulfur, and actually both of these will be our Brønsted-Lowry hydrogen atom that's going to be acidic. So, but again, standard definition of a Brønsted-Lowry acid is HA. Now, the names of common acids and bases are simply derived from the anions formed when they dissolved in water. Now, anions are things that are negatively charged, end with an "ide", and you add the prefix hydro and change the "ide" to the "ic" acid. So we have chloride. Now, chloride is going to be our anion, so it ends in an "ide". We've talked about this nomenclature in previous lectures. And we add the prefix hydro, and we change the "ide" to an "ic". So in this case, we have hydrochloric acid, or HCl. Because again, when this Brønsted-Lowry acid breaks apart, we produce the proton and the negatively charged chlorine. So we have the chloric part, hydro, and the acid because we know it's an acid. So that's in terms of nomenclature of how we name our acids, but we can have what we call polyatomic anions, so producing multiple. Now, in this case, sulfuric acid, H2SO4. SO4 is labeled sulfate, as you probably recognize from our lectures or our labs. Now, this ends in an 8, and so we change that 8 to "ic". So instead of sulfate, we change it to sulfuric acid. And then we have polyatomic ions whose names end in "ite", such as sulfite, SO3 2-, again, something we've seen a few times. We change the "ite" to an "us", so sulfite, and this would be H2SO3, be sulfurous acid. So just nomenclature in terms of how to name these. We're only going to work with a small subset of acids, like hydrochloric acid and sulfuric acid, but in terms of generalized naming, it's all about what the ion you're producing, and then is it a single ion like chloride, or is it a polyatomic anion such as sulfate or sulfite? You simply just change depending on what you have. Now, when we're thinking about what this physically looks like in terms of how many protons are being donated by an acid, a monoprotic acid contains a single acidic proton. So in the case we have here, hydrochloric acid, it can simply only donate one acidic proton. A diprotic acid has two acidic protons, as you can see with sulfuric acid here, H2, thus it can it can donate two acidic protons. And then finally, we have a triprotic acid, such as phosphoric acid, where we have 3 protons that can be donated as this acid breaks down. So you can pretty much sort of gauge what it's going to be simply just by how many hydrogens it has attached to its A group, right? Because the generalized form of a Brønsted-Lowry acid is HA. Now, our Brønsted-Lowry acid can also be neutral, or it may carry a net positive or negative charge. So in this case, hydrochloric acid is a net neutral charge. We can look at hydronium. We've talked about that before. It can be a Brønsted-Lowry acid. It carries a positive charge. Or I don't remember what this one's called off the top of my head. It carries a net negative charge. So it can be neutral, positive, or negatively charged. So those are our acids. Now, a Brønsted-Lowry base is a proton acceptor. So it has to have the capacity to form a bond with a hydrogen ion, right? That's all a proton is, just a single hydrogen ion. And a base itself has to contain a single lone pair of electrons that can be used to form a new bond with that proton. So we can look at water. It's going to be in this case, it'll be our Brønsted-Lowry acid. And then we have ammonia, NH3. It's going to be our Brønsted-Lowry base. Now you'll see that the ammonia has a free pair of electrons tacked onto the nitrogen, as we've seen before. Now, ammonia can act as a base because it has 2 free electrons, thus it has the capacity to accept a hydrogen from water. So ammonia becomes ammonium as it accepts that proton, and we produce the hydroxide ion, OH minus. So that's really the big definition here. Can you absorb something? And typically you need a lone pair of electrons, because you can't really just kind of absorb a hydrogen ion willy-nilly. You need electrons to share with that hydrogen, right? Because you need to be able to form a covalent bond. And what do you need to form a covalent bond? Well, you physically need lone pairs of electrons. Now, we typically can write our Brønsted-Lowry base B and then 2 free pair of electrons. Now, in this case, we have ammonia, which we would write just B, 2 dots, right? That's the generalized formula, right? For an acid, it was HA. For a base, it's simply B, 2 lone pairs of electrons. So we can see that with ammonia. We can see that with water. Now, oh, that's got a little bit jumbled up. Now, that's typically what we see, but in other cases, when we have metal salts such as sodium hydroxide or potassium hydroxide, the metal will essentially be essentially just forgotten, essentially in this case, and we're really looking at as the B would be our OHs here, because OHs have the capacity, because they have lone pairs, to accept to accept free protons from the area around it. So we can look at what this physically looks like, a generalized reaction of a Brønsted-Lowry acid with the Brønsted-Lowry base. We have HA reacts with B, giving us A and HB, with A being negatively charged, HB being positively charged. But you'll notice the acid loses its proton, and the base gains its proton, right? Because it was just simply B, now it's HB. So this is the generalized reaction by which we can see a reaction between an acid and a base. Now, when we look at this, the product formed by the loss of a proton from an acid is what we call its conjugate base, and the product formed by the gain of a proton from a base, by a base, is called its conjugate acid. Now, you'll notice that the arrows go both ways here, which means this reaction is reversible. And that's kind of how it works. When you dissolve an acid into a base, or you put them together, essentially, they form those conjugate bases and those conjugate acids, but the reaction is reversible. So it's kind of always bouncing back forth, right? Because you're creating an acid and a base. You're starting with an acid and a base, but you're also creating a base and you're creating an acid. So this reaction goes both ways, back and forth, because on both sides, you'll notice we have an acid base and then we have acid base. So they go back and forth. So we have a conjugate acid, conjugate base. Remember, the base is formed from the acid, and the acid is formed from the base. Because again, we're losing or gaining protons in this system of a Brønsted-Lowry base and acid. That's all it is, right? Now, let me give you a quick example of an actual chemical reaction. So we react hydrobromic acid, HBr, with water, which is going to be our base. You'll notice that the water gains a proton, becoming that hydronium ion. And bromine has lost its proton, becoming just a bromide ion. Now, in this case, the acid is hydrobromic acid, as its name implies. Our conjugate base from that is just the bromide ion, because again, it's a base, thus it has the capacity to absorb free protons. And bromide has the capacity to absorb free protons because it has extra electrons hanging around. Now, our water is again going to be our base because it has the capacity to absorb protons. By absorbing a proton, it thus becomes the hydronium ion. And because it has an extra hydrogen attached to it, and it has the capacity to lose that hydrogen, thus it is the conjugate base. So that's all you got to remember. Can it lose a proton or gain a proton? And whatever it can do, you define it as an acid or a base, respectively. Now, typically speaking, when a species does gain a proton, again, hydrogen ion, it gains a +1 charge. So in this case, the base form of our base, or I guess our initial form of our base of water, it's going to gain a proton, thus it becomes positively charged. Because again, we're adding a proton, we're not adding any electrons with it, so we're sort of skewing the charge, right? In this case, it's neutrally charged, which is cool. But by adding protons, we're making it slightly positively charged. Now, when a species loses a proton, it effectively gains a -1 charge. So hydrobromic acid, HBr, it loses a proton. Now bromine is negatively charged. Because again, it's losing a proton. It's not losing a hydrogen ion. I'm sorry, a hydrogen atom. It is losing just the proton. It's keeping the electron, but it's losing the proton. And up here, it's gaining a proton, but it's not gaining an electron with it. So important thing to remember, because when an acid reacts, it becomes negative. When a base reacts, it becomes positive. Now, there are special classifications under our Brønsted-Lowry acid-base system. We have what we call amphoteric compound. Don't try to say that fast. And this is simply a compound that contains both a hydrogen atom and a lone pair of electrons. Thus, it can either act as an acid or a base. So what does this look like? Now, when we add water, when we have water, we either start as just garden variety water. Now, if we added a proton to water, water becomes the conjugate acid, the hydronium ion, H3O+. So water is a base because it's, again, accepting that single proton. Now, conversely, water can act as an acid. Thus, it can shed a proton, again, just the proton, not the electrons. It sheds the proton and becomes OH minus, or the hydroxide ion. So it can either be, when we're thinking about an amphoteric compound, it can either be an acid or a base. It goes both ways in this situation. It can either gain or lose proton. Thus, it is both an acid and a base at the exact same time. It just depends on its conditions. So now, we've looked at water a couple times, right? We've looked at water with an acid, and we looked at water acting as a base. And it really depends on how strong the acid in the base is. If the acid is stronger than water, water will be the base. If the acid is weaker than water, water will be the acid. It just depends. Because acids and base physically have strength to them. Now, the splitting apart of a covalent or ionic compound into its ions is what we call dissociation. Just, you can think about dissociation just kind of falling apart, right? That's sort of the baseline definition of what dissociation means. Now, when a strong acid, such as hydrochloric acid, dissolves into water, 100% of the acid dissociates into ions. So what we can see here is hydrochloric acid reacts with water, forming the chloride ion and the hydroxide ion. Hydrochloric acid, the strong acid, water is going to be the base, conjugate base, conjugate acid. Now, in this case, if it's a strong acid, you'll notice that the arrow only goes one ways. And why is that? Well, the reality is because the acid is so much stronger than the base, it really favors the product at equilibrium. So when we sort of talked about how reactions are pushed, in this case, if you have a very strong acid, it pushes the reaction towards the products. Because again, hydrochloric acid, very, very strong acid. Now, again, and so just again, single arrow is used because it is technically reversible, but it's heavily favored towards being the products over the reactants just because of how strong hydrochloric acid is. Now, common strong acids that we're going to look at and you'll hear in average everyday life, iodic acid, hydrobromic acid, hydrochloric acid, sulfuric acid, and nitric acid, all really really common acids that you see. Like for instance, you guys have worked in the lab with hydrochloric acid, so it's pretty common. This is also the acid that your stomach produces to help dissolve your food. So that's a strong acid. Now, a weak acid, when it dissolves in water, only a small fraction of the acid will physically dissociate into those ions. So what we use to denote this is what we call unequal reaction arrows. Now you'll notice that we have the arrow going forward and we have a larger arrow going back. Now this implies that the strength of this chemical reaction is not very strong. What it's telling us by having the arrow facing the reactants being, the products being shorter than the arrow facing the reactants tells us that the reactants are going to be favored. So if we have this very weak acid, acetic acid, that reacts with water, we form hydronium and whatever this little friend here is called, I forget off the top of my head. But you'll notice that it does, because this is a very weak acid, and vinegar, acetic acid, is a very weak acid, it favors just staying as an acid in water. Now, common acids that we're going to see, carbonic acid, HCO3, it's pretty common. Hydrofluoric acid, relatively, weak. Phosphoric acid, relatively weak. And I forgot the hydrogen cyanide as a weak acid. So weak acids, again, they're simply just not dissolving enough. Right? They're just not strong enough to push the reaction forward, right? So strong acid, strong base. Now we can physically look at what this looks like, right? So in this case, we have the strong acid, hydrochloric acid, reacts with water, and we have the weak acid, acetic acid, reacting with water as well. Now you could just visually see the strong acid, HCl, there is no hydrochloric acid floating around. All we have is chloride ions. And you'll notice that we have hydronium ions hanging around as well. Thus, the acid is completely dissociated into the water. That's in contrast to our friend vinegar here, where you see there's a bunch of vinegar hanging around, and there's a few hydronium ions. So again, weak acid, strong acid fully dissociates, weak acid partially dissociates. Not fully, but partially. Now, very much like a strong acid, a strong base, when it dissolves in water, 100% of the base dissociates into ions. So in this case, we're looking at sodium hydroxide, NaOH, reacting with water, forming the sodium ion and the hydroxide ion. So in this cases, again, it's complete dissociation. The reaction arrow only goes one way here. Now, common strong bases that you've worked with in lab and you'll see in your textbook and stuff like that, sodium hydroxide and potassium hydroxide. You'll notice that they're metals bound to an OH, right? So this is what we have for strong ones. Now, when a weak base dissolves into water, very much like a weak acid, only a small fraction of the base disassociates into its ions. So in this case, we have ammonia reacting with water. We produce ammonium in the hydroxide ion. And you can see the arrow is much bigger heading towards the left than it is going towards the right. Thus, the reactants are favored over the products, making this a weak base, the exact same way a weak acid looks like. And again, conceptually, to see what this looks like, you'll notice sodium hydroxide dissolves in water completely. There's no sodium hydroxide here on the left. When ammonia dissolves, you'll notice that there's mostly ammonia, a little bit of ammonium, and a very small amount of hydroxide ions here. So again, exactly the same as our weak acid and strong acid counterparts, same thing for our bases. Does it dissolve fully or positively? Or I'm sorry, fully or partially. That's the word I was looking for. Now, a strong acid readily, so conceptually speaking, an acid is strong because it does readily donate a proton, and the conjugate base it then forms is very, very weak. So when hydrochloric acid donates its proton, the resulting chloride ion is thus a very weak base. A strong base readily accepts a proton, forming a very, very weak conjugate acid. So we have a very, very strong base, the hydroxide ion. When it absorbs a proton, it forms a very, very weak conjugate base of water. So just a sort of another way to think about what makes a strong acid, what makes a strong base, what makes a weak acid, what makes a weak base. And we can see some examples of these acids. So acids, we have hydrochloric acid, sulfuric acid, and nitric acid, all completely ionized in water, so they're considered very, very strong acids. You'll notice that their conjugate bases are very, very weak bases. On the other side, we have very strong bases, oxygen, free radical, a proton, and then a methyl group, CH3. Those are very, very strong bases. They form very, very weak acids. So, and then there's a in between, right? You have carbonic acid and so on and so forth. So, in terms of the scale, right. A weak acid produces a strong base, and a strong acid produces a weak base. So, just a handy way to conceptualize this on a spectrum, right? Because that's sort of how this exists. So when we're looking at a Brønsted-Lowry acid-base reaction, it represents essentially an equilibrium between the conjugate acid and its base and the conjugate base and its acid. So if we have HA reacting with B, that's supposed to be an arrow. I'm sorry, I don't know why it does that. We produce the conjugate acid and the conjugate base. Now, the position of equilibrium depends upon the strengths of the acids and bases, as we've discussed. If we have a weak acid, equilibrium favors the reactants. If we have a strong acid, equilibrium favors the products. Now, the other thing to note about this is that the stronger the acid reacts with stronger the base to form the weaker acid and the weaker base. So it's kind of a counterintuitive to what you would think, but if you react strong on this side, it creates weak on this side. Okay. So when the stronger acid and the stronger base are the reactants on the left side, so this side, stronger acid, stronger base, the reaction readily occurs and the reaction proceeds to the right and is favored to stay on the right. So as we discussed before, this larger arrow here, larger going forward, smaller going back, implies the reaction is at equilibrium, but it's not equal concentrations on both sides. It favors the weaker acid and the weaker base over the stronger acid and the stronger base. Now that's in contrast when we have a weak acid or a weak base. It favors equilibrium on the side of the reactants. So again, small arrow on the top saying there's less on this side, bigger arrow on the bottom saying that there's more on this side. But again, the arrows going back and forth tells you that it's at equilibrium, but it's at equilibrium on one side favoring the other. So again, a bit different from what we think about, right? Typically speaking, right? Because when we think about equilibrium, we're saying, previously speaking, not including today, but prior to today, when we talked about equilibrium, we were looking at arrows that were equally sized, right? Where the concentration was equal about on both sides. But today we're, again, having this slightly new way to look at equilibrium, where one side can be heavily favored over the other in the case of our acids and our bases. Now, let's do a quick problem. So how can we predict the directionality of equilibrium in an acid-base reaction? So the example we have here are the reactants or products favored in the following acid-base reaction? So we have uh, uh, hydrogen cyanide reacting with the hydroxide ion, producing CN and H2O. In this case, HCN is our acid, the hydroxide ion is the base. The base forms the conjugate acid, which is water, and hydrogen cyanide, being our acid, loses its proton, forming the conjugate base, Cn minus. Now, in this case, we have to identify the acid in the reactants and the conjugate acid in the products, which this figure has already done for us, and I just said. Our next step is determine the relative strength of the acid and the conjugate base. So if we go to, I have a little handy table here. Um, there's also tables in your textbook. They exist on the internet, and we have that little scale I showed you on a previous slide. We can see that HCN is a stronger acid than H2O. So in this case, we have the stronger acid on the left side, weaker acid on the right side. Thus, from what we know, if you have a stronger acid on this side versus this side, we know that the products will be favored over the reactants. Again, just because this acid is stronger than this acid, that's all. So whichever side has a stronger acid, it pushes it to the opposite side in terms of equilibrium. And we denote that with the larger size arrows. Conceptually speaking, right, if I have 10 of these, I'm going to have 20 of these, right? That's, just put in terms of straight numbers, right, with what these slightly unequal arrow sizes actually mean. Okay, so this brings us back to our friend K. Now, we talked about K last class. Our K, as you'll recall, is our equilibrium constant. Now, we're going to apply an equilibrium constant to our acids and our bases. So for the reaction, where an acid, HA, dissolves in water. So our acid, our base, our conjugate acid, and our conjugate base. So we have this reaction here. We calculate the equilibrium constant as written. K equals, remember the brackets equal concentrations. So the concentrations of the hydronium times A minus divided by the concentration of HA times the concentration of water. It's pretty fun, right? Now we can make this a little bit different. Now we can multiply both sides by the concentration of water, and it forms a new constant, which we call the acid dissociation constant, or K sub A, or Ka. So Ka equals K times water, or it equals to the concentration of the hydronium ion times the concentration of the conjugate base divided by the concentration of the acid. Now, conceptually, what did we do? All we did was multiply the water by both sides, thus we just got rid of water on the bottom, right? So it's not really all that different. But this is what we call Ka, or the acid dissociation constant, because typically speaking, we're thinking about acids dissolving in water. Right? I mean, that's what most liquids are made out of. Right? Now, when we think about conceptually what Ka means relative to our equation here, the stronger the acid, the larger Ka ends up being. And what this means conceptually is that equilibrium is favoring the formation of the weaker acid. In this case, on our equation, it's H3O, right? So when we have a very strong acid, Ka increases. Why is that? Well, let's go back to this equation. Ha, if it's a very strong acid, it's going to completely dissociate into its ion and its in the conjugate acid, right? Which should mean the concentration of HA in this equation would be very low, which makes our denominator very low, which pushes Ka higher, right? Which is kind of nice, right? So it's conceptually, not, I don't know, I don't know. It's conceptually it fits together nice, right? Because mathematically, when you calculate Ka for an acid, it's simply, the stronger the acid, the smaller the denominator, because more acid is dissolved, right? So the more acid, the stronger the more acid dissolved, the stronger the acid, thus the larger the Ka. And why is that? Because your denominator is getting smaller. So let's look at some of these Ka values for weak acids. So some of these acids we've talked about, like phosphoric acid and acetic acid. But you notice that we have Ka's values for weak acids, and you see that they're pretty small, right? For for instance, we've talked about acetic acid a bunch, and this is just vinegar. Acetic acid has a Ka value of 1.8 times 10 to the minus 5. So they get pretty small, but these are weak acids, very, very weak acids. Now, conversely, when we start to look at strong acids like hydrochloric acids, it's basically going to flip this on its head. We're going to have very, very high Ka values. But again, this is just Ka values for weak acids. But you'll notice that Ka increases as the acidity increases as well. That's what we just discussed. Now, water is, as we've sort of hinted at, but we haven't exactly said, can be a Brønsted-Lowry acid or a Brønsted-Lowry base. So water continues to be spectacular in terms of things it can do. Remember, water is amazing, right? It's not just like amazing because it gives life, but it's just amazing for all its crazy properties. Now, water can react together in an acid-base reaction. Water can act as an acid or a base. Thus, if we react two waters together, we can produce the conjugate base, i.e. the hydroxide ion, and the hydronium ion, H3O+. So we have our acid forming its base and its base forming its acid. Now, this happens, so when you drink water, you are drinking some, this reaction has occurred in your water, but you'll notice that the arrows heavily favor our reactants over our products, because water in this case is both a weak acid and a weak base, thus it favors being on this side. So the Ka of water is relatively low. So just something to think about. Now, from the reaction of two water molecules, we can write the following equilibrium expression. K equals the concentration of the hydronium divided times the concentration of hydroxide divided by the concentration of water times the concentration of water, or H2O squared. Now, very much like we did for the Ka, we can multiply both sides by water squared. Thus, we yield Kw, or the equilibrium constant of water. I'm sorry, the ion product constant of water, which is Kw, equals the concentration of hydronium times the concentration of hydroxide. So again, this is our ion product constant, or Kw. Now, experimentally, we can actually physically show what this looks like. Now, when you calculate the concentration of hydronium and hydroxide of water at 25 degrees C, so room temperature, so it's our standard temperature, right? The concentration of both of these ends up being 1.07, 1.0 times 10 to the minus 7 moles, or molar concentrations, right? This is, moles per liter, right? I'm sorry, grams per liter. Now, Kw, as we've mentioned, is H3O times HO, the concentrations of both. So it ends up being 1.07, 1.7, this number times this number, which gives us a Kw of 1 times 10 to the minus 14. Now, why is that important? Well, remember, as we've discussed, everything is pretty much, when we're thinking about acid-base reactions, we're thinking about this relative to water. So Kw, because everything's mostly in water anyways, is actually a constant. So Kw serves as a constant for us when we have aqueous solutions, so solutions in water at 25 degrees C. So we have Kw as a constant of 1.0 times 10 to the minus 14. Now, getting in a little bit more into how we physically use this mathematics. Now, we can calculate the concentration of hydroxide or hydronium when only one of them is physically known. Now, if we don't know the concentration of hydronium, we simply know that our equation, let me just hop back one slide, we know our equation is this. Thus, we can just rearrange mathematically this equation to calculate the concentration of this or this. Why? Because we know always Kw is equal to 1 times 10 to the minus 14. So the concentration of hydroxide ions is always equal to 1.04 times 10 to the minus 14 divided by the concentrations of hydronium. And we always know the concentration of hydronium is equal to 1 times 10 to the 14 divided by the concentration of hydroxide ions. Now you might think to yourself, why do we care about that? Well, it'll become very clear in just a few slides of why we care about this. Now, let's conceptually just look at what this looks like. Now, if we have concentration of hydronium ions in a cup of coffee is 1.1 times 10 to the minus 5 molar, then our hydroxide simply can be calculated by looking at OH equals Kw divided by the concentration of hydronium, which mathematically it's this divided by this. Now, when you're dividing exponents, you simply add this exponent to this exponent. That's really all you do. And you would also divide these two together, but that's, these are 1 divided by 1, so it's 1. But in this case, you'll just notice that if I add 5 to here, I add 5 to here, this goes from minus 14 to minus 9. So just in case if you don't like exponents, that's just a quick handy way to divide exponents. You simply just look at adding the denominator to both the top and the bottom, canceling out the bottom, and changing the exponent of the top. So what does this mean? Well, you see that the concentration of hydroxide ions is 1 times 10 to the minus 9. Now, in this case, you'll notice that the concentration of hydronium is greater than the concentration of hydroxide. Our hydronium is 10 to the minus 5. This is 10 to the minus 9, right? Minus 5 is bigger than minus 9, right? Because this is, as you increase your exponent here negatively, it becomes smaller and smaller, right? Like this is a 0 followed by, the decimal place followed by 9 zeros. And this is the decimal place followed by 5 zeros. So this is much bigger than this. So conceptually, this is larger in concentration than this. So what does this mean for this solution? Well, we interpret this when hydronium is greater concentration than hydroxide. We interpret this as being an overall acidic solution. It's kind of nice, right? You can use our concentration of one versus the other to calculate the acidity. Now, why is this more acidic? Well, remember, this is our conjugate acid. This is our conjugate base. If we have a strong acid, it dissociates completely into the conjugate base. Thus, we'd have a higher concentration of this. Thus, we started off with a very strong acid. Thus, we produce a higher concentration of the conjugate base. It's kind of nice conceptually, right? How that really works out, right? Now, we can look at this mathematically. Now we have the concentration of hydronium, so the conjugate the conjugate base, and hydroxide, the conjugate acid. Now, when we have a neutral solution, the concentration of hydronium equals the concentration of hydroxide. When we have an acidic solution, like we just looked at for coffee, hydronium is in greater concentration than hydroxide. And when we look at a basic solution, hydronium is in lesser concentration than hydroxide. So just a handy way, right? And these are the numbers that go into that, but this is kind of the important conceptual thing to think of. And why is it? Again, conjugate base, conjugate acid. The more of this, that means the more acid you had dissolved, thus the more acidic your solution is going to be, which is nice. Now, we have the concentration of hydronium. Now, this brings us to the pH scale, one of the coolest scales out there. Now, the lower the pH, the higher the concentration of hydronium. Why is that? Remember, hydronium is the conjugate base. So to get a high concentration of the conjugate base, we have to have an acid that dissociates very strongly in water, thus lowering the pH of the solution, driving the concentration of this higher and higher. So conceptually speaking, when we have an acidic solution, the pH is less than 7. When we have a neutral solution, the pH is equal to exactly 7. And we have a basic solution, the pH is greater than 7. Now, what that means in terms of the concentration of hydronium, for an acidic solution, the concentration of hydronium is greater than 10 to the minus 7. For a neutral solution, the concentration is equal to 10 to the minus 7. And for a basic solution, it is less than 10 to the minus 7. So we calculate the pH values by simply using this equation above. pH is equal to the negative log of the concentration of hydronium. Fun stuff. So let's look at this pH scale. And again, you've probably seen a pH scale at some point in your lifetime, but again, it's a really handy scale. Now, the pH scale is a 0 to 14 scale. Now, you can go below 0 and you can go above 14, but for the purposes of this class, we're thinking of that 0 to 14 scale. For the purposes of biology, it's a 0 to 14 scale as well, and medicine for that matter. So, neutral is 7. As we go from 7 down to 0, it's getting acidic. As we go from 7 to 14, it's getting much more basic. And you can see a number of different household common things. Milk is about neutral. Pure water is 7. Tomatoes are 4. Strawberries are 3. Lemons are 2. Sodas are about 2, right? Now, very strong things like, for instance, like antacids are pH of about 10. Ammonia or chlorine, which you might use for cleaning, are 10 and 11. So common things you know in your house fall on this pH scale. Now, the important thing to remember about the pH scale, when I change from 7 to 8 or 7 to 6, this is a logarithmic scale, right? Remember the equation, it's logarithmic. So every time I go up a pH unit or down a pH unit, the concentrations of hydronium ions changes by 10 times. So if I have 100 here, it goes up to 1,000, 1,000 to 10,000, to 100,000, so on and so forth, right? Every time you change a full unit on the scale, it's an order of magnitude times 10. So when we change the pH by 1, we're changing the concentration by 10 times. Because again, we calculate it with this number, which includes a logarithmic value. So a 1 to 2 is a 10-fold change in pH. That's a very important thing to remember. The pH scale, small changes matter. Even a fraction of a pH unit, 0.1, is a huge change. Huge. And so I've mentioned this. The pH scale is a logarithmic, so it has the same number of places after the decimal as there is units in the original number. Well, if the concentration of hydronium ions is 1.2 times 10 to the minus 5 molar for a given solution, we could calculate its pH. Now, what we do is we take our equation, pH equals negative log of the concentration of hydronium. We substitute in the hydronium. Now, mathematically, how do we actually physically handle that? Well, it depends on how comfortable you are with logarithmic values. So it really depends. You could do this in a calculator if you so chose. That's probably my guess as how most of you would handle this. But when you take the logarithmic value of this value, so 1.2 times 10 to the minus 5, you end up getting minus 4.2. Now, generally speaking, when you have a minus sign and your exponent, you're going to get a negative number when you take the logarithmic value of it, just as a note. Now, for instance, if we had 1 times 10 to the minus 5, the value would here be minus 5, just as a note. Now, when we take the logarithmic of this value, we get negative 4.92. Now, we have the negative times the negative, which gives us a positive. So in this case, again, our concentration is this. We solve the equation, but again, it's the negative log. So you can think of writing this equation also as minus 1 times log of this value, if you felt like it. But when you are calculating pH, you got to remember to multiply the minus versus your calculated value. And so in this case, if we have this concentration of hydronium, we end up getting a pH value of 4.92. The solution has to be acidic because the pH is less than 7. Because remember, anything less than a pH of 7 has to be acidic. So conversely, we can do the opposite of this math. Now, if a pH, what is the pH of the solution? That is 8. I'm sorry, what is the concentration of hydronium if the solution is 8.5 for the pH value? Well, we take our handy dandy equation, but this time we have our friend 8.5. Now, 8.5 equals the negative log of the concentration of the hydronium ions. Well, what do we do? Well, how do we get rid of a log? Well, we have to take the anti-log. Now, log goes, if I have 10 to the minus 5, it takes me to 10, right? It takes me just to 5, minus 5. Now, the anti-log does exactly the opposite that. It essentially expands this out. So it's, in this case, we take the anti-log of both sides, we take a negative of both sides. So we went from negative log, now we're at minus 8.5 equals log of hydronium. And then we take the anti-log of both sides, thus giving us the concentration of hydronium on there, and the anti-log of minus 8.5 there, which allows us to calculate the concentration of hydronium, which gives us 3.2 times 10 to the minus 9 molar concentration of hydronium. Now, if we go back to our handy dandy scale from a few slides ago, we're not going to do that, but you can. The solution ends up becoming basic because the concentration of hydronium is greater than 1.7 times 1 times 10 to the minus 7 molar concentration. So we can work both ways. We can give you a concentration and you can calculate a pH, or I can give you a pH and have you calculate a concentration. Same math, same equation. It just, if you don't feel comfortable with logs, it's kind of, this is something you would have learned like a long time ago. So if you're not comfortable with logs, doing it in your calculator is equally as fine. This isn't really a math class, so I don't want to spend too much time showing you guys how to calculate logs. So I'm going to refer you to the internet as a better source than me to how to teach you how to do math, because I am not a math teacher by any stretch of the imagination here. Now, when we bring this pH scale back to the body, now I've mentioned before, in your stomach, you use hydrochloric acid to dissolve your food, or at least partially dissolve your food. Now, the pH of your stomach, because of all the hydrochloric acid, has a pH of 1.6 to 1.8. But you'll notice that your pH varies pretty heavily across your body. Your blood is pretty consistently at 7.4. Your large intestine is between 5 and 7. Your pee is between 4.6 and 8. Your small intestine is about 8 and 5. Your saliva is typically acidic, being between 5.8 and 7.1. Fun fact about your saliva, it changes depending on what you're drinking or what you're eating. So your saliva becomes very acidic after you eat a very sugary food, or if you drink a very acidic drink. So if you drink a soda can, that's like a double whammy, because you get all the sugar in the soda and you get the acidity of the carbonated water in the soda. So kind of a fun thing. The rest of your body, the pH values are pretty consistent. They don't change a ton. They have a little bit of a range, but they don't change meaningfully quickly like your saliva does. So, all right. So that's how we calculate pH. That's the pH scale. That's what an acid and base is. Now let's look at some more in-depth acid-base reactions. Now this one will be this one will be familiar. Now this one is what we call a neutralization reaction. Now this is when an acid and base that produces a salt and a water as a product. So what this looks like conceptually, we have an acid, HA, reacting with a base, M being a metal, so it could be like sodium, OH. This produces water, and the salt, Ma. Right? So in this case, the acid, it donates its proton to the hydroxide, forming the water, and then the anion, A minus, combines with the cation, M plus, to form the salt, Ma. So we're basically just swapping pieces, right? You can think of this almost like as like a double substitution reaction, right? That we discussed, what, I don't know, over a month ago now. But again, we're swapping the H with the M. That's all we're really doing in a neutralization reaction. We're swapping, right? So we're not producing, in a true sense, a conjugate acid and a conjugate base, but we're producing a water and a salt. So let's look at this Now we're going to write a balanced equation for the reaction of magnesium hydroxide, MgOH2, that reacts with hydrochloric acid. So this is what the equation looks like. HCl reacts with magnesium hydroxide, producing water and our salt. Now, what we want to do here is identify the acid and the base. Now, we know hydrochloric acid is, as its name implies, it's an acid, and magnesium hydroxide is going to be our base. So that's fun. Now, next thing from that, we're going to determine the structure of our salt. Now, the salt, again, is formed from the parts of the acid and the parts of the base that are simply not used to form the water. Well, what parts of the acid are used for the acid, right? Well, remember, the proton is the acidic part, right? So that's going to be react with the water, right? That's what acids do, right? They donate that proton. Now, what do bases do? Remember, bases have the general formula, B with 2 pairs of electrons. In this case, our base is simply not going to be MgOH, but it's just simply going to be the OH. Not MgOH, but just the OH. Remember, that's B with 2 free electrons. Now, that's our base. That's our acid. Remember, those two are going to simply react together. H plus 2OH gives us water. So that's fun. What we're left with in this equation, if we're doing our math right, we're left with the chloride ion, so the cation, I'm sorry, the anion here, and we're left with the magnesium cation here. Okay, that's all we're left with, right? So back to this equation, HCl with MgOH2. We know that the OH and the H have to react together to form water. That's what we know, right? So we're left with just magnesium and chlorine. Now we see chlorine has a -1 charge, magnesium has a +2 charge, which together, if we're going to balance this out, if we're going to balance the charges out, we have to have 2 chlorines for every magnesium, thus creating a neutrally charged molecule. So we can write out this full equation. Hydrochloric acid reacts with magnesium hydroxide, producing water and magnesium chloride. Now, you'll notice that we have, if we didn't have these, oh my goodness, I'm forgetting the name. I can't remember the technical name, I'm sorry. If we have these numbers, I'm sorry, these coefficients in front of here, right? This equation wouldn't be balanced. So we need to make sure we balance this equation, just like we've done in the past. We need to make sure we balance this equation. Now, in this case, we would need 2 moles of hydrochloric acid for every mole of magnesium hydroxide, which on the other side would produce 2 moles of water and 1 mole of magnesium chloride. Or, you can think of it as 2 molecules, 1 molecule, 2 molecules, 1 molecule. Doesn't really matter how you think about it. But again, it's all got to be equal proportions. We've got to balance the number of molecules on this side with the molecules on this side as well. Now, so that's a neutralization reaction. Now we can write what we call a net ionic equation, which contains only the species involved in the reaction. Well, what does that exactly mean? Well, we know with an acid and a base, all we're really thinking about is the protons and the acceptors, right? So we can just simplify this reaction. Hydrochloric acid reacts with sodium hydroxide. Just as a note, this reacts pretty violently. Very strong base, very strong acid. That reacts pretty violently, just as a note, which produces water, H2O, and sodium chloride. Now, we don't need all this other stuff at the end of the day, right? Because, well, we know we have hydrogen ion that's going to be produced. We know we have a chlorine ion that's going to be produced. We have a sodium ion that's going to be produced. And we have a hydroxide ion that's going to be produced. So we really can just simplify this by omitting these, what we call spectator ions. We don't really care about the sodium or the chlorine. We really only care what's happening to the protons, right? And the acceptors, right? The B in our Brønsted-Lowry base. So we can really take this equation and simplify it as hydrogen plus hydroxide gives us water. That's it. Right? So we're just omitting the sodium and the chlorine here simplifies this equation. So you'll commonly see acid-base reactions written as the simplified form. Because again, this is all that's really happening, right? you don't really care about the formation of the salt. You really only care about what's happening with the protons. Now, give you example of this sort of well, give you another example, I should say. Now we can look at what's called a bicarbonate base, HCO3, and this will react with one proton to form carbonic acid, H2CO3. Carbonic acid is pretty common. Now, you see this carbonic acid is in the ocean. You see carbonic acid in your soda as well, just as a note. Now, this reaction looks like this: proton, HCO3, producing carbonic acid. Sleepy this morning. And further, this carbonic acid will dissociate into water and CO2. So that's fun. Now this sort of reaction, if you run it in reverse, so water combining with CO2 can actually form carbonic acid. So this is actually what happens in your soda cans, right? So when you add CO2 to a soda or a seltzer, right, it lowers the pH of your soda. Well, why is that? Well, CO2 is reacting with water to produce carbonic acid. Another common reaction we see is a carbonate base, CO3 2- reaction with two protons to form carbonic acid as well. So two protons reacting with carbonate, forming H2CO3, which can then decompose into H2CO2. So we can look at this as an example: two hydrochloric acids reacting with sodium carbonate, producing sodium chloride and carbonic acid. And remember, carbonic acid can then dissociate into water and CO2 as well. Carbonic acid is a relatively weak acid. So we're looking at things that are salty, right? Sodium chloride, salt. Now, the acidity of these salt solutions is kind of interesting. Now, a salt can form from an acidic base or a neutral solution, depending on whether its cation and anion are derived from a strong or weak acid and base. So if we have an arbitrary salt, which we note as M, because remember, a salt is just simply a metal, like sodium or potassium, attached to a negatively charged thing like chlorine or bromine or something like that. So we donate a salt, M+, A-. The cation, M+, comes from the base, and the anion, A-, has to come from the acid. Right? So let's look at this conceptually. Now we have sodium chloride. Sodium chloride, if we have the reaction of sodium hydroxide, NaOH, reacting with hydrochloric acid, we see sodium hydroxide is a strong base, HCl is a strong acid. Now, one of the products they form is sodium chloride, as we've looked at this reaction before, right? The chlorine has to come from the strong acid, and the sodium has to come from the strong base. Now, what's left over? H2O, right? The hydrogen and the hydroxide. Right? So we looked at this equation before. Now, interestingly enough, a salt that is derived from a very strong base and a strong acid reacting together will form a net neutral solution. Just kind of handy. So if you mix sodium hydroxide with hydrochloric acid in equal amounts, they will form a neutral solution, which is kind of cool, right? And why is that? Well, they're dissociating completely, right? They're strong and strong. That means they dissociate completely. And what we produce is going to be equal concentrations. So it ends up making it neutral. Now, a salt that's derived from a strong base reacting with a weak acid does form a basic solution or a pH greater than 7. So if we look at sodium hydroxide, which again is a very strong base, it's reacting with carbonic acid here. This is a weak acid. When those two react together, they form sodium carbonate. No, that's not right. It doesn't matter what it's called. NaHCO3. This is going to, because this is much stronger than this, it's going to form a net basic solution. Why is that? Because this is just so much stronger than this. Now, the converse also exists. When we have a weak base, such as ammonia or ammonium, and we have a strong acid like our friend hydrochloric acid, He's our friend through all this. They produce ammonium chloride, NH4Cl. Now, hydrochloric acid is strong, ammonia is weak. Thus, the salt that's derived from this, NH4Cl, will thus be a slightly acidic solution, so the pH will be less than 7. And you can look at this conceptually as a table if you'd like to. Strong base, strong acid produces a neutral solution. Strong base, weak acid, basic solution. And weak base, strong acid produces acidic solution. Now it's kind of, conceptually makes sense, right? If I have a strong acid, it's going to push things to a pH that's lower. If I have a strong base, it's going to push the pH up, right? So, but that being said, if you have a strong and a strong, they cancel each other out, producing a neutral solution. So, one of the things that we're going to do next semester, if you take Chemistry 2 with me, is a process called titration. Now, titration is used to determine the concentration of an acid or a base in a solution. It's very straightforward. Now, if you want to know the concentration of an acid or a base, if you want to know the concentration of an acid, you add a base of known concentration until the acid is simply neutralized, i.e. it brings the pH to 7. So, conceptually speaking, this ends up equaling the number of moles of acid has to equal the number of moles of the base when the acid is physically neutralized. So if we think about this, if we have some unknown concentration of hydrochloric acid and we add sodium hydroxide, a strong base, we have to keep adding sodium hydroxide until the pH gets to 7, because that means that both are in equal concentrations to one another. Now, once equilibrium is maintained, or neutralization occurs, I should say, this is what we call the endpoint of titration. And conceptually, you can look at this. We have an acid, we're adding a base to it of known concentration. We keep adding and adding and adding. Now, in this case, we have a pH indicator, so it's changing color depending on the pH. And in this case, we get to the end point where the solution is completely purple, thus implying that the pH is net neutral, i.e. it is a pH of 7. And conceptually, what this looks like is we determine the unknown molarity from titration data. It requires 3 operations. So first we take the volume of the base that we're adding. Now we use the M, so molarity is equal to moles divided by liters to calculate the number of moles of the base that we added. Then we convert the moles of a base to the moles of an acid. And then we we know that how many moles of the acid we have. Then we use the volume of the acid to get the molarity of our acid. So nice little handy flowchart, just a couple quick and simple conversions. So let's walk through what we have. Now, the question we're going to ask from a titration data set is, what is the molarity of hydrochloric acid solution if we add 22.5 milliliters of 0.1 molar sodium hydroxide solution, and that's how much we need to titrate a 25 milliliter sample of this acid. So our known quantities are volume of the base, concentration of the base, and volume of the acid, but we don't know the concentration of the acid, and that's what we want to find out. So step 1, we determine the number of moles of the base needed to neutralize the acid. Now, remember, molarity, big M, is simply equal to moles divided by liters. Now, we know the molar concentration. So again, we started off with our concentration of sodium hydroxide, 0.1 molar. Now, we just use this equation. We have 22.5 milliliters of sodium hydroxide. We know that is equal to 1 liter over 1,000 milliliters, right, times 0.1 moles of sodium hydroxide over 1 liter. That's the moles to liter conversion factor. But again, this is moles to liter, we have milliliters. So we have to convert them. And when all that math is said and done, we get 0.00225 moles of sodium hydroxide. So that's our moles of the base. Now, we make the assumption that the moles of the base, if we get to a neutralization point, are equal to moles of the acid. we do this little conversion, but really all we're doing is just saying, if I have this many moles of the base, I have this many moles of the acid. So I end up having 0.00225 moles of hydrochloric acid. So that's fun. And then we simply want to calculate the molarity of our hydrochloric acid. Well, remember, molarity is moles divided by liter. So we just add what we know. We calculated the molarity, the moles of hydrochloric acid. We know the volume of hydrochloric acid. This is in milliliters, so we have to add a conversion factor here. And we ultimately get 0.09 moles of molar concentration of hydrochloric acid. So again, conceptually, we started with this, we're finishing with this. Just a couple quick conversions to get what we need from titration data. Now, sort of to wrap up this, we're going to talk about a few just quick topics. Now, we have what's called a buffer. Now, a buffer is a solution whose pH changes very little when an acid or bases is added. Now, a buffer is typically a solution that is composed of roughly equal amounts of a weak acid and the salt of its conjugate base. Well, why does that make sense? Well, a buffer resists a change in pH because the added base, because remember we always write bases typically as hydroxide ions, will react with the weak acid, and the added hydronium, which again comes from donating a proton from the acid to water, will react with the conjugate base. So as we're producing hydroxide, and hydronium essentially just reacts with what is contained in the buffer to minimize the amount of pH change. And that's really it. So let's conceptually look at this. So in this case, we have water and we have hydrochloric acid. pH of water is 7. pH of hydrochloric acid is 1.7. Now, when we add when we add water, when we add sodium hydroxide to the water, it changes the pH pretty dramatically. When we add hydrochloric acid to the water, it changes the pH pretty dramatically. So 7 to 1.7, 7 to 12.3. Because again, adding a base here, in this case, we're adding an acid. Now, when we have a buffer present, things are a bit different, right? The buffer has a pH of 4.74. Now, when we add hydrochloric acid to this buffer, you'll notice that the buffer only changes by 0.4 on the pH scale. Now, when we add sodium hydroxide, you'll notice that the pH of the buffer goes from 4.74 up to 4.77. Pretty big difference, right? The pH up here went up by 5. Here it went down by almost 6. Here it's changing by fractions. And why is that? Because the buffer is absorbing parts of the acid and parts of the base, thus minimizing the pH change. So it's kind of fun, right? Buffers can really strongly minimize how much pH change. Now, if an acid is added to the following buffer equilibrium, then the excess acid will react with the conjugate base, so the overall pH simply doesn't change. Now, if we increase the concentration of our friend acetic acid, now acetic acid is reacting with water in this case, producing hydronium and CH3COO, conjugate base, conjugate acid. Now, if we add more of this, it will drive the reaction one way or the other. So buffers minimize how much we're physically changing, which is kind of nice. And the same thing for the base. I'm just going to skip over that. And here's some common buffers that we see out there: acetic acid, acetate, bicarbonate, hydrogen phosphate, dihydrogen phosphate. So these are just common ones. Here's their Ka values. Here's their weak acid and their conjugate base that they add to become buffers. I'm just going to skip over this. And so I wanted to just wrap up just by focusing on the human body. Now, as I mentioned, the human body has a consistent pH of about 7.4. Now, when we think about the human, I should say the human blood, not the human body. We saw the human body, right? Its pH varies pretty dramatically. Now, the normal blood pH is between 7.35 and 7.45. Now, inside your blood, the principal buffer is carbonic acid, H2CO3, and bicarbonate, HCO3. Cool, right? Now, what this looks like, HCO2 reacts with water to produce H2CO3, and then with water present, H2CO3 reacts to perform H3O and bicarbonate. So in this case, we're always adding CO2, right? Because CO2 is constantly being produced by metabolic processes. And so thus the amount of CO2 that you produce is directly related to the pH of your blood. However, because you have those buffers present, your pH remains relatively consistent. However, you can have what's called acidosis, or in this case, we're talking about respiratory acidosis. Now, this results when the body fails to eliminate enough CO2 in the blood. Now, respiratory acidosis as a condition leads to lung disease or complete lung failure. But again, we're adding more CO2, thus we're increasing the concentration of hydronium and bicarbonate. So we're driving this reaction forward because we're increasing CO2, thus we're making our blood more acidic. Now the opposite of that is respiratory alkalosis, which is caused by hyperventilating. Is faster. Oh, I disconnected. Sorry about that. I guess I just disconnected for a brief second. Let me start to slide over again because this is our last slide. So respiratory alkalosis is caused by hyperventilating. Now, this is because very little CO2 is being produced by the body because you're taking in so much outside air. So CO2 is going down, so it's pushing this reaction the opposite way, thus increasing the pH of your blood because you're having less hydronium. So it's kind of cool, right? So have this relationship between how fast you breathe or how little you breathe in and how acidic your blood is. Now, extended time with alkalosis or acidosis will, as my slides told you, can cause you to be dead. Being too high of pH or too low of pH can be a very deadly thing for the human body in terms of the pH of the blood. All right, that was a lot of pH stuff. I'm gonna stop recording.